Okay, so part 2 here, and the goal will be for us to make it through all the examples today and give you a couple practice problems, but rewrite each expression in simplest form. We're taking the cubed root of 135. In other words, try to simplify that root. Do the same thing here. Okay? I want you to talk to your neighbor about how you're going to do A and B there. Best you can. Okay. Hey, can I have your attention back up here? Hey, root 135, the cubed root of it, we're trying to break that down into a perfect cube. 135 is not a perfect cube. However, a perfect cube that goes into it, if you think back to your list of perfect cubes you made yesterday, okay, is 27. The cubed root of 27 times the cubed root of 5 makes 135. 27 times 5 is 135. Then you just put your cubed root symbols. Cubed root of 27 becomes 3. And this is not a perfect cube, so we just leave it. So that drops down, and we get 3 cubed root 5. So you've just simplified it. Okay? All right. Take that. Okay. Letter B. What's the problem with that? They do have different bases. The radical is in the denominator. So let's take a look at these rules real quick. An expression involving a radical with index n is in simplest form when these 3 conditions are met. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions. No radicals appear in the denominator. Okay? Radicand. All right? Those 3 things. All right? So, to meet the last 2 conditions, you have to do what we call rationalizing the denominator, which involves multiplying both the numerator and denominator by an appropriate form of 1. That creates a perfect nth power in the denominator. Okay, what all that means, okay, is first, no radicand has a perfect nth power as a factor other than 1. That's what happened here. This is my nth power. It has a perfect nth power as a factor. Therefore, we took that out. Okay? The second one, no radicand contains fractions. In other words, this could have been, now we don't want to actually write it like this because we are actually making it even a less simplified problem. But this could actually be that. Okay? The 5th root of 7/8. Now, that is a fraction under the radicand. Okay? And the last one is no radicand appears in the denominator of the fraction. So from here, you would usually drop back to this form and you go, well, now I have a problem because I have a radicand in the denominator. And the way you get rid of that is to do this last thing. Rationalize the denominator, which you've done in the past. If you've had me or Vogel, we've always talked about that as multiplying by the special number 1. The number 1 is just saying, I am going to multiply this thing, this fraction, by itself. Now, it doesn't always work like that when you're dealing with other degrees. So what you've learned in the past is like if we had root 5 over root 2, you'd say, well, I just multiply by root 2 over root 2, which gives me 2 on the bottom, because that's root 4. The whole point of multiplying there is to get that special perfect square. Root 4, which is 2, and this is root 10. Now I've fulfilled this situation. I don't have a radical in the denominator. I'm good. Okay? In this, I can't do that. Because if I multiply by root 5, or excuse me, the 5th root of 8, okay, well now I have the 5th root of 64. And 64 is not a it's not a perfect root when you're dealing with an index of 5. Okay? I can't find the 5th root of 64 to get a perfect number. So what I need to start thinking about, go ahead, Emily. I could. So if I did that and I go, well, okay, I'll split that up into the 5th root of 32. and the 5th root of 2. That's fine because this one's perfect. It gives me 2, but I still am stuck with this on the bottom. Okay, but you've kind of come up with the answer there. It'd be nice for this to become 32. Right? So what could I multiply the bottom by to get that to be a perfect 5th root? 4. So if I multiply this by the 5th root of 4, then that gives me the 5th root of 32, which is what we want. We want a perfect 5th root there. And remember, it's multiplying by 1. We can't just randomly change the value of our fraction. The only number you could multiply and not change the value of your number is 1. That means if this is the 5th root of 4, this has to be the 5th root of 4. Because this value right here is 1. Okay, so now I have the 5th root of 28 on top. That's kind of blurry. That's a little less blurry. Okay, what is the 5th root of 32? 2. And this is the 5th root of 28, which there's no other perfect root that will go into that in terms of the 5th root there. So we're good. Okay. Everyone rate themselves 1 to 5. It's not easy. It's brand new for a lot of you, okay? But you have to kind of hold on to those branches that you remember from the past. That's this stuff. Okay? All right. Questions? All right, let's try this one here. This is the next one on your page. Example 4, write 5 plus root 3 in simplest form. First, tell your neighbor what's wrong with that. Okay, what's the problem? Radical in the denominator. Any thoughts on how to do that? Okay. Well, there's this thing called the conjugate. Okay, the conjugate of 5 plus root 3. Conjugate's up here. I'll write it up here. Okay. When you multiply something by its conjugate, the conjugate of 5 plus root 3 is 5 minus root 3. So I am going to multiply by 5 minus root 3. And remember, it has to be in the form of 1, so whatever I have on the bottom, I have to have on the top, so that's 1. Now, tell your neighbor why that is even helpful. Once again, this is applying something you already know. The reason it's helpful. Okay, for those of you struggling, hey, a plus 2 and a minus 2. What do we call that? It's the difference of two perfect squares. That gives me a squared minus that number squared, which is 4. Okay, now how is that helpful when applied here? Well, notice my first term is 5. 5 squared is 25. And it's plus and minus. This is a difference of 2 squared is root 9, which is 3. So that is 25 minus 3. Okay, so that just pulled the radical out there. I am now left with 22 on the bottom. And on the top, I'm left with 1 times 5 minus root 3, or just 5 minus root 3. I now have that in simplest form. And the word conjugate just sounds cool. All right. Questions? Yeah? Root 3 times root 3 is root 9. And the square root of 9 is 3. Okay, moving on. Next one, I want you to take a look at this set right here. Hopefully the next set of problems on your paper. Is that true?
Yes.
Yes, woohoo! I want you to simplify. Go ahead and work with your groupies. Please. All right. Hey, this is a fourth root of 10. There's one of those, and there's 7 fourth roots of 10, so that gives me 8 fourth roots of 10. We're just counting up the fourth roots of 10. Okay? Now, if 10 was a perfect root, okay, if it was a perfect fourth root, then we could simplify that, but it is not. Therefore, we are done. Okay? Questions there? Okay, so it's just kind of like combining like terms. These are like roots. This is the fifth root of 8 and the fifth root of 8. So I have 2 here and 10 here. So I have a total of 12 times 8 to the 1/5 power, which is the same thing as fifth root. I cannot multiply 12 by 8 because I would not be following the order operations. I have to do the exponent first. Yes, Roy? Sure, yeah, like that. That would be fine. Okay? And this guy here, notice cubed root, however, they're not the same. So we can't just combine them. We can't say, hey, well, that's cube root of 52. That doesn't work. It's like trying to combine x's and y's. That's not going to work. So what should I do? Megan? Good. Cube root of 27 and the cube root of 2. That will work. That gives me cube root of 27 is 3. Not quite. Because now I have 3 cube root of 2 and then that cube root of 2. So you have 3 cube roots of 2 and 1 cube roots of 2. So you have 2 cube roots of 2. Total G's. Pretty radical.
Every joke, every time, anyone, always.
All right. Questions? Okay, let's give you some practice problems. I want you to do 5 through 12 there on the bottom of the page, reviewing those skills we just covered. See how you do. First 3 there. There we've got them. Check your work out. Let me know if you have questions as I walk around. Check out the next 3 here. Well, looks like my work on that one kind of blended in. Here, let's go to 8 and 9. We'll get 8 and 9. Okay? The fifth root of 24 over 2 is number 8. I tried to put a bunch of different steps there, but you got to break that fraction into root 3 over root 4. The fifth root of 3 over fifth root of 4. Then multiply by fifth root of 8 times fifth root of 8 so that you can get that fifth root of 32 there. Okay, so here's your special number 1. Okay, which gives you the fifth root of 24, or the fifth root of 32, and the fifth root of 32 is 2. Questions on 8? Number 9, you multiply by this conjugate. Now keep in mind that when you do that, here's your special number 1. There's really parentheses holding that together. So when you go 3 times this, it has to be 3 times 6, which is 18, and then 3 times root 2, which is 3 root 2. And then you get squared, 36, and the squared is 2. Okay, difference of 2 squares. So root 18 plus 3 root 2 over 36 minus root 2, that actually is 18 plus 3 root 2 over 34. I guess I was just hiding, saving the ending. Suspense, that's right. Thank you. All right. And number 10, just subtracting them. This is like having a 1 right here. So we get 7 minus that 1. Okay? All right, last two there. I kind of have quite a bit of work for 11. I stepped it out quite a bit. Now, 11, add them up, you get 12 and times 9 to the 2/3. Now, some of you would stop right there, but really, 12 times 9 to the 2/3, you can go 12 and 9 squared, and then factor out that 1/3, which gives you 81. And the benefit of that, you could then break that down. Right? So if you're thinking of it in terms of cubed roots, if we're looking at that one in terms of cubed roots, you think of this as 12 times the cubed root of 81. And then you could break apart the cubed root, right? That's the cubed root of 27 and the cubed root of 3. And times 12, and that's 12 times, this is 3 then, and the cubed root of 3. It's just, from there, this part becomes 36, and cubed root 3. We're just leaving it in the fraction form because it started in fraction form with the exponent versus radical form. So if it starts in exponential, leave it in exponential at the end. But if you want to switch it in the middle to root form so that it helps you out, you definitely can. Tom, you watching one of my video lessons right now?
No, I'm trying to do the math behind it.
Oh, okay. I just did it in my head, dude. Oh, okay. Nice.
No, like,
Oh.
you get the 1/3 out of the 9 2/3, and then have to get the square off of that.
Well, from here to here, you mean?
Yeah.
Yeah. So when you're factoring out a 1/3, this you can think of 9 to the 2/3 as that's the same as 9 to the 1/3 plus 1/3. Right. That gives you 2/3. Okay. Okay, so you're just factoring out a 1/3 power. So if I were to, maybe we approach this a different way. If I were to bring this back in, I'd multiply this by this, which would give me 2/3. So since I can multiply to bring that in, I could actually pull that out as well. Okay. Well, hey, when you try these today on your practice, if you're struggling on them, make sure you come in. We can talk. Don't just be good because you're like, all right, I need to be good. Okay. All right. But I doubt you'll find it on your calculator. Okay. Number 12. Got to simplify. So this is root 8 and root 5. That gives you a perfect cube. And then that's 2. Okay, cubed root of 5, and then we can add those up. This would be like having a 1 out here. So 1 plus 2.
That's what I said.
She's just joking. Okay. All right. Hey, let's move on. Example 6. Woohoo!
Yay! So happy!
Simplify. Should be simple. It's in the name. Okay, give it a shot. Okay, so some of you picked it up really fast, but those of you struggling, try to break it apart first. Okay? Try to break 2 pieces inside apart and write them separately and then simplify. Okay, cubed root of 64 is 4. Now, when I'm dealing with the cubed root of x to the 6th, one way to think about this, really, if I'm dealing with the cubed root of, not x to the 6th, but y to the 6th, this is saying what thing times itself 3 times will make x, or y to the 6th. I keep going x. Okay? So I could think of that at y to the 6th as y times y times y times y times y times y. Do I get the right number there? That's very true. 6 times. Okay? It's a good math joke right there. Well done. I'm very proud. Okay? So when I'm doing that, this tells me how many groupings of y's I need. Right? So that means my answer is, each grouping is a y squared. Okay? That is what that factors to. 4y squared. Total O. 3 O's actually. Okay. No. Yes, Rory. Yeah, very true. If this was like y to the 7th, you just had a y hanging out there, you'd have to put a cube root y at the end. Yep. Yeah.
So you're just kind of like dividing, and could you just look at the y to the 6th?
Yep. Yeah, so the other way to think about it, good, the other way to think about it, applying it to what we're learning, is you could rewrite this as 6 over 3. Y to the 6 over 3 power, which is y squared. Okay, that's really the shortcut, right? So if you're trying to make conceptual understanding of what's happening here, this is it. But mathematically, the shortcut is just to write this in exponential form and then divide the two. Okay? That's kind of the quick route on it. So if I'm looking at this and I'm kind of applying what Zach just said there, so this would be, first let's break it up. X to the 4th, the 4th root of x to the 4th, and the 4th root of y to the 8th. I could rewrite that exponentially as, rather than the 4th root of x to the 4th, that's x to the 4 over 4, which is x to the 1st, or just x. Okay, and this one right here is y to the, 8 over 4, which is y squared. Okay? Just remember that this number is your denominator and the inside is your numerator. Okay? If you're struggling with that, once again, you could think of how, if I have x, 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 and x, and that number says how many groups I have to have. Well, I have to have 4 groups. Well, each one of those would form a group, so that would be x to the 1st. And this would be y, 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 y. And yes, Walsh, it does make you ask why. Okay, and 2, 4, 6, 8. Each one's a squared, so you go there. Okay? All right, questions? So try example number 7. So Roy, this is going to kind of take into account a little of what you were talking about, I think. Okay? Guys, letter A first. Okay, I'm not going to go through the other ones yet, but let's look at a letter A here. And I'm not going to group them right now, but if that's helping you, go for it. Okay, but when I'm looking at this, I'm going to break each apart. That's the 5th root of 4, the 5th root of a to the 8th, the 5th root of b to the 14th, and the 5th root of c to the 5th. All right, well, when I continue with that there, this 4, I'm never going to take the 5th root of, so I'm done right there. That's a dead end. I'm done. I'm stopping. Okay, circle it and move on. 5th root of a to the 8th. Okay, one way to do it is to think of it exponentially. That's a to the 8/5, and ask yourself, how many 5s go into 8? 1. Okay, so we go with 1. How many do you have left? Yeah, 3. And those 3 have to stay inside the radical. They don't get to come out and play. Okay, you have 1. That means that's an a to the 5th that a right there, that if you want to think of it this way, you could say, well, that's a to the 5th. You can break it apart like that. And by having this piece break down to that, you could pull this out. The 5th root of a to the 5th is a. So you pull it out there, get rid of it there. No matter how you think of it, you end up with the result of a to the 5th, a times the 5th root of a. Now we're done with that piece. Oh, a cubed, thank you. All right. So if we kind of go the same route here, we could kind of break this apart. B to the 14/5. How many times? 2. And B to the 4th inside. And then this one just becomes C. They cancel. Okay? So now if we look at all of our circles there, everything in the radical, since they're all the same root, we're going to put all under the same root. So we have a 4. We have an a cubed. Thank you. We have a 4, an a cubed, and a b to the 4th. And on the outside we have a, and I forgot my b squared, or b squared. Okay, and c. Totally yeah. Well, I'm glad. Okay. Letter B. What's nice about B? Hey, does this cubed and this 8 help us out?
Yeah.
I mean, 8 is a perfect cube, right?
So it's just 2 plus squared?
Remember, when you're dealing with variables, it's different, right? We would really want this to be a 6 if it was perfect. Yeah. It's a good idea. The cubed root of something that will make that perfect. Yeah, so by... I didn't hear what you said.
Why does a third inside the radical, and then would that make it 3? I don't know how to explain it.
So let's go it this way. If I think of this as y to the 8/3, what does 3 go into evenly? Closest to 8. 9. So we'd need one more.
Oh, but we added it?
Mm-hmm. So this would be y to the 1st. Okay? Hey, by doing that, you get the cubed root of y to the 9th on bottom and x cubed root y on top. And the cubed root of y to the 9th is y cubed. So x cubed root y times y cubed. Okay, so it sometimes helps to see it in fraction form there. Okay? Moving on, letter C. Give it a go, letter C. Hey, if you're struggling, ladies and gentlemen, can I have your attention back up here? 14 and 2. Start by taking care of that. That's 7. Notice I have negative exponents, but I have x's on the bottom and y on the top, a z here. This z, when it's a negative exponent, it moves up. Okay? The x's I can deal with by, when I'm dividing the same base, what do I do with the powers? I subtract them. So I have 7, and I have x to the 1st power minus the 3/4 power. I then have y to the 1/3 and z to the 6th. That's not my answer. What's wrong with that? Yeah, so what is that? X to the 1/4, y to the 1/3, and z to the 6th. That is my answer. Hey, remember, that's already simplified because there's no radical in the denominator. Okay, there's no radical under a fraction. And you can't find a perfect fourth degree that goes into x, third degree into y. Okay, so we're good. All right, your assignment is to finish that page. Okay, now, that means you have to do example 8. Eyes here, please. You have to do example 8. Let me fold this over so you... This is what you have to finish. Those 4 problems. Okay? Yes, those 6 problems. I was looking down. I'm not good with numbers sometimes. That's bad news for you guys. All right? Very good. Advanced students correcting me. Good job. All right. Very good.